So thank you for having me here today. I'm going to go ahead and leap right into it. So my talk's going to be split into two parts. The first part is building on part of Micah's presentation, as she noted, and her work, and also Steve and his graduate student, Jared Callahan. And what attracted me to that project, this Dynamical Regimes project, is this kind of perspective of looking backward at how we made scientific advances in the past and trying to use that as inspiration for how you might set up machine learning approaches. And then, so I'll go through that, and then the second part of the talk will be a little bit of speculation about where we might go and sources of inspiration for maybe new architectures. Okay, so as Micah had said and Steve yesterday, when we talk about dominant dynamical regimes, we're typically referring to an empirical situation where you're looking at non-asymptotic equations, where you, a non-asymptotic reduction of equations. So you're going to throw out some terms in a way that doesn't have nice numerical properties, but really is more aligned with how fluid dynamicists 100 years ago would say, okay, I'm going to estimate these characteristic scales. That gives me a non-dimensional number. And using that, I can eliminate some of these terms from my the model that I'm going to build. And this project is with my colleagues at Los Alamos, Juan Sainz and Daniel Livescu, and also with Micah. And it's funded through the Machine Learning for Turbulence research effort at Los Alamos. So, like I said, going back many years ago, not exactly 100, but back to the 1950s, this is a classic example from oceanography. Monk, there's also a Stommel version of this type of idea. Monk took the barotropic vorticity budget for the ocean and was looking at it at a time when we had virtually no simulation data and very sparse observations, and using sometimes assumptions of convenience, sometimes geometric assumptions, and also empirical scaling assumptions. He reduced the barotropic vorticity equation to a three-term balance between wind stress, advection of planetary vorticity, and a diffusion of vorticity model. And so when he did that, what he got was this box model for the North Pacific, and what it showed is you get this internal sphere drip gyre circulation, and at the boundary you get this diffusive boundary layer. So those are effectively two different regimes in the way that we're using the word regime. Another example of this was brought up by Steve yesterday, and so going back to the early part of the 20th century, people had wind tunnel data and things like that on turbulent boundary layers, and over a period of something like 26 years, this cartoon emerged of different dominant balances within this spatially developing turbulent boundary layer. And the way that that happened was very kind of ad hoc. So what I mean by that is that there was no universal criteria for estimating how they were going to truncate their equation terms in different regions of the flow. The way this normally happened, like I was saying before, is by using non-dimensional parameters like Reynolds number and things like that, and other ways of scaling the equations. And so they would usually start out by partitioning the flow. So I'm going to follow the human column here in the middle and say, okay, so if you look at this turbulent flow, let's look at the statistics of it. I can see that in the free stream, there's no turbulence, and then in this boundary layer, there's a lot of wiggles. So right there, someone can use a simple integral length scale, something like that, to define a boundary to a different regime. And then, so then the next step would be to select a hypothesis for that regime. So what do I mean by hypothesis? In this case, it's a binary set, so terms are either on or off. And so, like I was saying, people would use scaling estimates for that. And then finally, the way they would test those hypotheses in the third step down here is to usually build some kind of model. They would model the terms they kept. And then if that actually, that model was predictive, in some sense, they would assume the scaling that allowed them to throw away the other terms was good. And since this was all done, 100 years ago, that was that knowledge became canonical for fluid dynamicists. And that's why I think there was never really a emphasis on developing a universal criteria for checking that kind of equation reduction. So building on work by Micah and her colleagues from 2019, and also Jared Callahan, who was a student with Steve, you can take this alternate route using unsupervised machine learning, in this case, clustering, so no neural networks. And I think everyone kind of understands unsupervised learning now, the difference between unsupervised and supervised. So if you go that route, first thing you do is you can use a clustering algorithm to partition the data. Second, you can apply dimensionality reduction to, within each cluster, label the terms as ones or zeros, on or off. So that part was mentioned yesterday in Steve's talk. If you remember the colored boxes he showed, those were representing on and off terms, or ones and zeros. And then finally, the part that I'm going to talk about here is this hypothesis testing. So how do we know that you have chosen the right parameters, as was just asked in the last talk? And so what we've done is come up with a verification criteria. So you can go back, you can turn the knobs, and keep looping over the algorithm parameters, and then finally get a result that you have some confidence is better than other algorithm parameter choices. I think you can't necessarily say it's global unless you search the entire infinite space of parameters. So just to back up a second to what I mean by clustering. As Micah mentioned a few moments ago, we're not clustering in physical space, we're clustering in the space of the equation terms. So if I take an equation that's just say a plus b, and say a and b are both functions of x and y, so take the top row. So if I randomly distribute a and b, that's what's shown in the top two left plots. And then I can run any clustering algorithm that you like. There's, I don't know, something like 100 of them now. You can explore that on scikit-learn if you're curious. It's a good code repository for that in Python. So then you run a clustering, and what's being plotted is in the third column, you have A versus B. And I used hierarchical density-based scan, which is a non-parametric clustering algorithm. This one allows you to eliminate noise, which is why you see 3 clusters, and then the black dots, those have been labeled as noise. That's just an artifact of the clustering algorithm. If I had chosen something like k-means, it would label, there would only be 3 colors over the whole thing. And then, so it's labeled these blobs because they're there's a coherence to them in terms of their density. And then you can project the labels back out onto X and Y space, which is shown in the top right. So you see the same kind of random pattern in where those, where each cluster is. So you can do the same exercise in the bottom row, but now I've distributed A and B as a kind of flag, I don't know, like a French flag kind of configuration. And so you see when you cluster in the space of the equation terms, it looks pretty much the same. And then when you project it back out, you see that flag kind of design again. So that's just a subtlety to this idea of clustering an equation space that I want to make pretty clear. So the next step is to take your, say we have equation terms for one of those clusters. And imagine we're talking about zonal momentum, the zonal momentum equation on an F-plane. So I've written all those terms up on top, and we're going to run a dimensionality reduction algorithm. So Jared and Steve had proposed using sparse principal component analysis, which is hard to present with a mask on. Anyway, so if you run SBCA, if the numbers are the values of those terms, are such that geostrophic balance is being described, then what it will do is, based on how you choose your regression, your lasso regression coefficient, it'll set some terms to 0 and others to 1. So in this case, if you have, geostrophy present on the scale that your data is collected, then you'll get something like this H, where there's just the ones correspond to the Coriolis term and the pressure gradient. And so then the next step is to say, okay, how do we know that that hypothesis actually fits the data? So what we came up with is this optimization problem, so which is defined in this third equation down. And basically what we're saying is that if your verification score, so if the fit of your hypotheses to the actual data is greater than the score would be if you kept all the terms, then you should neglect some. And if that's not the case, you should keep them all. So what is that score, which we've labeled with the V here? So it's a weighted average over your data of this metric, which is, we call it the magnitude score. So here the subscript n refers to the nth grid point. So what you're doing is taking this scalar value for at each grid point, which we called gamma, which would be the magnitude gap. So you can take log 10 of the smallest term in the set of the ones that corresponds to the ones, so the on terms. So the smallest term that you're going to keep, and the difference between that and the largest of the terms you're neglecting. So that's your magnitude gap. And then we enforce a penalty here where, so in this case, there's only 2 terms that are on. But what if you have 5? And you could have a many orders of magnitude within those 5. So we put in a penalty that penalizes the case where you might have many orders of magnitude within the set that you've chosen to keep. So this is consistent with these kind of back of the envelope scaling estimates. And so I'll show you a little bit about how it applies in practice. So first, we can take an analytical problem, like using the method of matched asymptotic expansions. You can use a monk-like barotropic vorticity budget to get this solution, which is shown in plot A on the left. So that analytical solution, the colored lines are the equation terms that pop out of that solution. The black line is the error, the expansion error. And basically what you can do is then for every point, I can calculate that magnitude score for different hypotheses. So that's shown on the right in plot B. So as you move in X, what you see is there's a score between 0 and 1 for the purple line. Excuse me. Anyway, so you had mic problems and I have like breathing problems. Anyway, so you start out with the purple, and there we've said, okay, so the advection of planetary vorticity and the diffusive term balance in this the purple color hypothesis. So that has non-zero scores within the boundary layer, because if you look at the solutions, that's what you'd expect. Those terms are balancing. And likewise, if you go outside of that, look at this kind of sphere-Drippian type balance between the wind stress and the advection of planetary vorticity. So when you give a global score, that V term, which I had on the last slide, you sum that up according to a weighted average. So in this case, if it's 1D, that would be an X, but it can be 2D, be something like an area. And if you include time, you can kind of do this in any dimension that you want. So I've done spatial examples here, but there's no reason why you're limited to space. So to go back to the example from Micah's presentation, ran this algorithm on her problem using the her echo, the barotropic vorticity equation estimated from echo data, and I got very similar results in the sense that the dominant terms that were picked out and the And the shape of the results when you project back out onto the globe are very similar to her results. So one major difference is that this particular scoring doesn't account for the sign. So if you have 3 terms, you could have different arrangements of the sign of those terms, but in this case, they're all going to be get together. So you'd have to, I think, cluster again, or do something else if you wanted to split up by sign. So that's a kind of possible future work which we haven't addressed yet. And I did the same exercise here with, so on the top, we're using a Gaussian mixture model, which is a type of clustering, parametric clustering. On the bottom, we're using non-parametric clustering, density-based scan. And what we got was these results, physically, they both make some sense. You see things like wind-driven, the wind-driven gyre balance, Faradaysian type balance, but over large areas of the ocean. But the one on the top scores better. So this tells you, if I was just going to run at this problem without knowing what I was looking for, this would tell me that the top plot is the better one to keep. Yeah. Okay, and now to shift completely to a totally different type of PDE. This is a nonlinear diffusion problem in tumor angiogenesis, which basically in the plot E on the left, on the y-axis is a vein, and then the tumor is where it's labeled, and you have these things called endothelial cells that through nonlinear diffusion grow towards the tumor. And so you can run this on that problem, which has, it's a PDE with 7 terms, and what you get is this, it shows you on the right plot that the red cluster and the blue cluster, maybe a little bit of the purple, are dominant near the that front where the endothelial cells are growing the fastest. And that's a problem in oncology because you don't want those endothelial cells to get to the tumor, because then they build veins and vascularize the tumor. So okay, so then to return to Steve's problem, or one that he mentioned, the turbulent boundary layer. So here on the left in plot H, I'm showing this sort of your loss landscape. So that metric, the verification criteria, what you're looking for is the maxima as a function of alpha, which is the lasso regression coefficient, if you're using SPCA for dimensionality reduction. And then K here is the number of clusters. So that's prescribed. You choose K-means or Gaussian mixture model. And so if you just pick the highest scoring value at K equals 8, alpha is 50, you get this best score, and these balances that fluid dynamicists know and love pop out, and you get this the same kind of distribution that Steve showed yesterday for the turbulent boundary layer. So one question, so now we've kind of established that you can trust this, this scoring to give you an objective way to know which clustering algorithm to use, which dimensionality reduction to choose, et cetera. Then the question is, how big a problem can I apply this to? So anyway, so on the plot, I'm showing the time complexity as a function of the number of grid points. So basically, all of the things that we played around with here. So I'm comparing K-means clustering and hierarchical density-based scan. And then for dimensionality reduction, I'm comparing sparse principal component analysis with combinatorial hypothesis selection, which is combinatorial hypothesis selection is just a kind of brute force. I'm going to guess at every hypothesis there is. So that is not well. I put the complexity problem in the name because you're just you're guessing that way. So there's no parameters that you have to tune, no regression coefficient. But at the same time, if you have a large number of equation terms, it becomes a bit problematic computationally. But that's shown on the right. So, I have to catch my breath by going too fast. I've never presented an N95 before, and it's like, yeah, I'm kind of tempted to, but I don't want to. You sound great. You can't tell you're out of breath. Okay, I feel I'm like sucking down air. At least the mic works for, knock on wood. So on the right, this is the computational complexity in the number of equation terms. So the black line in both cases is the basically n log n, which is what everyone kind of aims for in complexity analyses. And so if you're better than that, you're great. If you're steeper than that, it's not a very good thing for scaling. And this shows, like we would expect, that the combinatorial guessing of hypotheses doesn't scale well if you have an equation with a large number of terms. But the advantage is you don't have another coefficient that you have to loop over, or algorithm parameter. So just to conclude that part, we basically formulated this partitioning classification of dominant dynamical regimes as an optimization problem. And I think you could also take that verification criteria and build and use it for a neural network based approach like UNets or things like that. Oh, thank you. Yeah, actually, that would be great. And so this verification criteria we proposed, based on the examples that we went through, it's consistent with our domain knowledge for those examples. And it also, because of the fact that it is in itself interpretable and objective, gives you a way to go to approach problems where you don't necessarily know the dominant dynamical regimes ahead of time. So next, I'm going to kind of, ask you to sort of indulge me in a little bit of speculation. But something that's come up a lot in this conference is these words generalizability and interpretability in the context of machine learning. And I think that both of them kind of get at this underlying idea for us as scientists of, well, I'll argue that it gets at causal inference that's expressed symbolically. I think that's ultimately what we want as scientists. Like if we think about scientific intelligence, typically, at least the scientists that we give Nobel Prizes to, they're very skilled at generating falsifiable causal models of nature in the forms of symbolic hypotheses and theories. And by symbolic, I'm referring to language, code, mathematics, any of those things. I mean, it's sort of the importance of symbols in science seems very clear, given that we communicate entirely through symbols. And so, in thinking about how AGI folks, or artificial general intelligence, which is this sort of, now it's a subset of AI, it was kind of the original intention of the field of AI back in the 50s when it started, which is, the idea is trying to make a sort of synthetic human out of a machine. I think that's something that we as scientists can avoid in terms of thinking about how you would build a machine that is better and better at science. I think there's no need to sort of get into that kind of sci-fi, because we have the scientific method, which is effectively an algorithm at our disposal, and we're really primarily interested in, like I said, causal inference that's expressed symbolically. So there's a lot of different definitions of intelligence, particularly in the AI community, I'm showing here, but they tend to talk a lot about, this general ability to acquire skills. And that's, of course, a noble research effort, and we benefit from those efforts. But I think there's a gap between their interests and our interests. So I started thinking about this after reading Cynthia Rudin's paper, which was this Stop Explaining Black Box Machining Models for High Stakes Decisions, use interpretable models. So that was in the context of sociology and criminology, but she put this plot in that paper, which I thought was really interesting, and I've kind of modified a bit. But the basic idea was that she had pulled this from a DARPA report, and she pointed out that these light blue dots actually were a cartoon. They didn't correspond to any real data. And she said that this is kind of taken as sort of like an implicit law in machine learning, that as you have this trade-off between predictive skill and interpretability. And her argument was that we don't actually have to build models that way. We could build models other ways. And I think if you try to build models other ways, you get into other thorny issues, in particular computational complexity. I mean, I think one of the great things about neural networks is their efficiency. So I put an example here of maybe the most celebrated machine learning algorithm in science, or deep learning algorithm, AlphaFold, which takes amino acids and then predicts protein structures from that. And it's got superhuman accuracy in its predictions. But it has some other issues where, this gets at the interpretability issue, where, so Alan Furst, who's a, prominent molecular biologist, has said, who worked on the project, has said that, solving the pathway of protein folding along with the dynamics is a different challenge than just predicting the protein structure. And so I think after kind of meditating on this a bit, I've come to the conclusion that I think that machine learning's role is primarily as a statistical association tool within science. And I think that's incredibly powerful, and it's also incredibly efficient. But it has limitations for the role, if the goal is causal inference that's symbolically expressed. So here is this is referencing a paper called Intriguing Properties of Neural Networks from 2014. And this paper pointed out this kind of interesting associative property of in image classification, and there's various other papers on this theme that have emerged since. So in the left-hand column of both of these squares is an image that's been, a network has been trained on these images on the MNEST database, and it labels these images correctly. And then through this kind of adversarial noise, which is in the middle column, so it's just this very small amplitude perturbations, they add the noise in the middle column to the left column, and that gives you the right column. So it's very hard for us to tell the difference between the right column and the left, but the right columns are all labeled ostrich. Okay, thank you. This to me is not something that I think is, I didn't put this up here to disparage neural networks. I put this up here just to illustrate that concept learning is a little bit different from statistical learning. I think concept learning, at least for scientists, has to do with causality expressed symbolically. So I'm really glad that Jakob presented earlier today as well, because he talked at length about Judea Pearl's efforts on causal inference. And so this is from one of Pearl's more recent papers. And so he talks about these kind of three levels of three theoretical levels of hierarchy, hierarchical approaches to causal inference, which I don't necessarily think they're hierarchical. I think that they each have a role to play. So the first is association. This is all, comes from a statistical type approach. So he gives us all as conditional probabilities. So the probability of y given x. Then there's this intervention level, which is the probability of y given you do something to x. So for scientists or anyone who's interested in causality, this is experiments, right? And then the other level, counterfactuals, this is really what I would call reasoning and logic, where if I have some fact that I know, can I then, build on that? So like an example, an extreme example that would be, not possible for a machine right now, but you think about Einstein and special relativity. So in his chasing light thought experiment, he imagined himself moving at the speed of light. So that came from this idea of relative velocity. And then he noticed that, okay, well, relative velocity gives me a contradiction. And the only way that I can resolve that is if I break this notion of simultaneity. Time must be relative. So that kind of logic, though, I think is doable by machines, maybe not the visualization. Out of breath. Okay, so like I was saying before, even though that sounds very high-minded and maybe sci-fi-ish, I think we don't have to wait until AGI happens in 2040, which is what the AI community gives a 50% chance of it happening. There are people now like Gary Marcus who are talking about ways to combine neural networks and machine learning, like these state-of-the-art machine learning methods with symbolic logic. So of particular interest is in that kind of physical reasoning core of the Venn diagram. And I think similar, you can make an analogy between doing a DNS of the entire climate and this idea that some people in the deep learning community have, that if we just have a big enough neural network, consciousness and everything else will just emerge. Maybe so, but we probably will never get there to simulate that. So it's a little bit beside the point for us. And I think that we can build symbols into our machines maybe before that. So just to give a couple examples of what I think machine scientists could look like. So the basic idea here is that you input prior knowledge and data, you output symbolic theories and hypotheses, you're iterating, so there's an iterating over experiments or over new data, and there's some aspect of symbolic logic happening, deduction. So one example of that is this AI physicist by Wu and Tegmark. So they used certain kind of data, but they're giving it this environmental data. It might do this divide and conquer. It'll split up the domain based on kind of partitioning ideas, and then it'll fit theories to those different regimes, I guess you could call them, using symbolic regression, neural network-based symbolic regression. And then they'll look for simpler solutions or see if they could unify this one symbolic expression for the whole domain. And they'll loop over that theory hub to try to find the best set of symbolic expressions for the data. So that's kind of one example. There's some other challenges that are, I think, that's probably way more than there really are, but those are just what I could put down. And then two other examples of this, since I'm running out of time. One is Yohide et al. Did this, they built a robot that uses causal inference to decide how best to make a cup of coffee kind of thing, or open a cabinet and pull out a cup. So what it'll do is it'll use virtual reality and run these kind of simulations along with these causal hypotheses. And then it'll also be rewarded if it doesn't fall over or break the cup. But the basic idea is that it's iterating and using logic in combination with machine learning. And then an older example is this functional genomicist robot by King et al. Although this doesn't include any machine learning, it's purely symbolic. And in that case, it was trying to identify these gene encodings that cause certain yeast proteins, and it was kind of basically using logic to choose what experiment to do next. So those are just examples. So yeah, I'm interested in I haven't done work in neural symbolic computing, but I'm very much interested. So if anyone wants to reach out or continue the discussion on those kind of crazy ideas, I'm definitely available. Thank you.
Thank you, Bryan. Thank you for the very thought-provoking talk. Any questions for Bryan? Yeah, Petra.
Yeah, thanks for the great talk. So at the beginning, you were using the clustering methods, and the clustering methods usually use some sort of distance metric, like Euclidean distance or Manhattan. So does that have an impact, like the choice of the distance metric? Does it have an impact on the results? And can there be something based on the physics that could be used for as a distance metric?
Yeah, so it absolutely has an impact on the results. So that was kind of, here, there's the dimensionality reduction happening as well, but here you can see the results are very different, and they're two very, very different clustering algorithms. This one, makes no assumptions of Gaussianity in your blobs effectively, and that one does. So it absolutely affects the results. As far as the physics of it, I think that's harder to answer that question. I would imagine that if you were looking at a data set that maybe you had some intuition that there'd be, Gaussianness in the blobs from the physics, but that's harder. That's kind of a stretch. Yeah. I didn't try that, but I would imagine that it would. And that was kind of the point here, was that we were giving a way to tell, which results are better. Yeah. But one thing I did notice on that front was that it mattered, you needed to standardize before using this, which is something that's, general best practice, but that applies here as well.
Any other questions for Bryan? Thanks.
Yeah, go ahead.
Thanks for the great talk. So my question is, a lot of us are using neural networks to emulate highly complex nonlinear functions, but it's also not trivial to use a neural network to perfectly match a very trivial function like identity function or simple polynomials. So if we want true generalizability, do you think we need to master the composability of neural networks that can do these simple tasks so that we can figure out like a chain of processes that you can turn into an actual causal inference down the road? I don't know if that question made any sense, but.
I can take a stab. So I guess, were you kind of asking about how you'd combine methods?
More so for true generalizability, just being sure that, say if you have like a lot of linear transformations followed by my nonlinear activation functions, those actually correspond to, or can correspond to, a more elegant equation that you're trying to emulate. Because with the training data, you can get your neural network to arbitrarily be arbitrarily close, provided enough training and hyperparameter tuning, but you're always not sure if it will generalize the test data. And the difference between that and using like a more theoretical approach of equations is that you have way more confidence in generalizability of basic science, of fundamental laws of physics. So how do you like bridge that gap appropriately?
Yeah, so that made me think about Naveed's talk yesterday, where he said that, kind of everything is data driven. Like, and I guess on a philosophical level, I guess you could argue that every person is data driven in some sense, that your brain is in a vat and you're taking in information. But I tend to think of data driven as separate from forms of logic. So in Pearl's hierarchy, I guess I would say, like, Pearl, I think, would argue that you shouldn't expect anything to work outside of the training data, or not very far, or that you are maybe lucky if it does, because he would argue that you need to have some kind of hypothesis testing, because that allows you to eliminate confounding. Because really what you're asking is, if there's confounding in your data, that's the real problem, is if you train on one data set, you're assuming there's no confounding in what your objective is. And then if there is in fact confounding factors in the test data, then you're going to miss the target. And so I think that's where Pearl is arguing that you need to do experiments or add more data and kind of loop in a sense, to get at, or the same thing with what Jakob was talking about, those directed graphs. You know, when you do an experiment, you can then check whether that graph, that causality goes one way, or there's two ways, or there's another factor. Yeah, and then I think on top of that, yeah, I'll stop there. Yeah,
Thanks.
Yeah.
Quick question, just because you mentioned standardizing. I was curious about how you standardized in your case when there were positive and negative values, and if that was a consideration or an issue at all for you for your input of your training data. Simple question.
So that wasn't a consideration. Well, so there wasn't training data because the clustering doesn't, I mean, it doesn't train, it more fits. So they were standardized just by subtracting the mean and divided by the standard deviation. So the signs were preserved for the clustering algorithm, and where the signs were thrown out was just in the final scoring. The verification score was only part of it that didn't consider the sign. Yeah.
So I had a more philosophical question, I guess, based on the slide about the prediction skill versus interpretability. Yeah, so here, I guess, I mean, the quote you said was we should use interpretable methods, but I mean, in our field, a lot of decisions are also made from model forecasts or from weather forecasts or even climate projections, right? So where would the balance be, would you say, in terms of, yes, we need interpretability to either address our own scientific curiosity or to improve our models by understanding why the machine learning model is working the way it is. But we also need high prediction skill to make decisions, right? And in those applications, the stakeholders don't care as much about interpretability. So I guess, like, just a personal opinion on what you would say in terms of community development of deep learning applications for Earth system. Do you think we should take both routes? We should take one of them?
I definitely think it's both. I think this is like a yes and situation, because I mean, so AlphaFold doesn't give you some kind of information, but it does make superhuman predictions, which is incredibly important for I think drug discovery and other things. So I think that's great that there is high predictive skill algorithms that maybe have low interpretability. I was just making the argument that, you know, as scientists, we kind of live, you know, hopefully if you write comprehensible papers, you live on the right-hand side of that. And so for us, I think it's worth it to try to think about, like Micah said, it's not obvious how to define interpretable. And in fact, in this paper, Cynthia Rudin mentions that interpretability is kind of domain specific. Right. So I'm really not necessarily arguing here for any kind of one answer or one, you know, thing that fits every situation, but just pointing out that, like, we as scientists, it behooves us to define interpretability for our field and then to develop methods, which I think are very not obvious. I mean, neural networks, as everyone has been talking about, are incredibly complicated. It's not obvious how to necessarily make that interpretable. So yeah, it's all of the above. Yeah.
Right. Exactly. Okay, great. I think it's time for our break. We'll come back in 30 minutes, back to this room. Thank you.